There, I'll start the recording and say happy Thursday. Welcome back to the basement. So thank you all for your flexibility. I should mention that on days where I have to teach on Zoom at the last minute, our classroom is still open. So if you want to go and like sit in there and Zoom from there, if you don't have another place to be, if you're on campus or whatnot, be my guest. My son's
I
doing
am
reasonably
there.
well. So yeah, I figured, like, I thought it looked familiar with the ceiling tiles actually. So my as I mentioned in my email, my son is homesick today, and normally that would mean that his dad would take care of him and I'd go to campus. But his dad is not only out of town; he is the outest of town I think you can possibly be. He is currently in South Korea for a conference. So we joke every morning we talk to him over breakfast, and he tells us about the future because he's 14 hours ahead of us, and so we say goodnight to him as he says good morning to us. Fortunately, he'll be back this weekend. I have on tap lecture 3 to start with. I had asked this for folks who were here earlier, but I'll ask it again. Any homework questions that I can help with at the moment? It is due Wednesday, so you've got almost a full week to work on it still. And I've been backing up the database every day, sometimes multiple times, just to make sure that nothing's going to go awry this time. So far, everything seems to be just fine. All right, no questions? All right, well, shall we get into it then? Why not? And I will continue monitoring the doorbell. Let me move this thingy out of the way. There we go. So, Unit 3. Building on what we've learned to try to examine more complex relationships between predictors and outcomes. So, where we're headed? Pictures. I know not everyone likes equations, right? But pictures are usually fun. Yeah. Not everyone, I said. I know some folks do. You know, we all have ways of thinking about the world, and like I think of the world through spreadsheets usually. Like I have sort of rows and columns in my head of information. They don't necessarily conform to matrices, but they're definitely spreadsheets. Another way that you can express these same kinds of general linear models is with a picture like this. This in particular is called a path diagram. And for more complex versions of the models, this can be a much easier way to communicate what your model has in it than just staring at an equation. So for instance, this is showing variables in boxes, so columns in your data set. I have 3 different generic x's here and 1 generic y. Each of the arrows going from a box to another box means you are predicting an outcome. So the box the arrow goes into is your y, where it comes from is your x. These are also known as exogenous in the path modeling literature, whereas y's are endogenous. You don't need to know those words yet. Path analysis, by the way, is something we cover at the end of the generalized linear modeling course, so you will get a chance to see that if you come back in the spring. The coefficients, the betas here, are labeling the slopes then that go from each x to each y. And this triangle thing with a 1 in it is a convention used to allow the fixed intercept to be part of the picture. If you were to represent a linear model here, which is right here, y sub I equals beta 0 as my fixed intercept plus a slope for each of my 3 predictors plus my e residual for how wrong I am. Note there's nothing multiplying beta 0, but if you were to write this out in its matrix representation to make the math work, you would essentially have to add a 1 here so that beta 0 has something to multiply, and that's the idea of the triangle. So it's representing what would be a column of 1s if you wrote it out as if beta 0 were multiplying a variable. So we are going to be adding predictors to our models, and 2 different contexts for this. So in this case here, just reviewing terminology, y outcome, other folks might call that a dependent variable, or DV for short, the criterion, and more generally, it is the thing that you are trying to explain or predict or account for. Predictors then, synonyms that people would use for that, is a regressor, an independent variable, or IV, typically if it's a manipulated variable, or a covariate if it's quantitative or someone else cares about it who's not you. And this unit is going to talk about using multiple predictors to describe one concept. So if you have a variable that its relationship requires more than one slope to describe how it relates to an outcome. That's what this unit is about. Unit 4 is going to be different variables, each of which could require more than one slope in describing an outcome. So what we are doing in terms of describing the end goal of this process is we are examining the effects of the X predictors on the Y outcome. So like these are the words that I would put into a results section to describe what I was doing. You will also hear it written backwards. People will sometimes say, I'm going to regress Y on X. I don't like saying it that way. To me, it sounds counterintuitive. But I put that out there because that's an equally correct way to express what we're doing. So how about a little review? Does that work for folks? I should assume that you have imperfect recall of every word that's ever been said. I think that's fair. Yeah, especially at 2 in the afternoon when it's getting towards like nap time. There's that post-lunch kind of slump sometimes. Not for me. I'm heavily caffeinated because being Dr. Mommy takes more concentration than usual. Just went upstairs, made sure my son had his Tylenol. He doesn't drink it voluntarily. I left it for him at lunchtime and I'm like, did you take your Tylenol, pal? Anywho, empty model. That's where we started from. This one is a baseline. It is the worst we can do in terms of predicting each person's outcome because an empty model has nothing but an intercept that says everybody gets the same prediction. That intercept is the mean of Y. So we're saying everybody gets the mean and E is how wrong we are. So at that stage, the variability across persons of the E residuals, or what we call residual variance, is all the variability in Y. That's our starting point. Once we add a predictor, then what should happen is that the variability of these E's across people should go down. It should be decreased. We should be less wrong in predicting Y now that we've accounted for some other piece of information, X, as our predictor. The interpretation of our fixed effects is going to change a little bit. So in the empty model, beta 0 was the grand mean of Y, the overall mean, Y bar as people call it in notation. Down here, beta 0 is a conditional mean, meaning that it is conditioned on X. Beta 0 is the expected value of our outcome when X is 0. For that reason, we would typically want to rescale X so that 0 is somewhere within the span of the variable if it's not already. So if 0 is already a meaningful quantity, you can leave it alone. This would be a concern if 0 is an impossible value relative to the rest of the scale of your variable. Beta 1, that's our slope. That is how the outcome changes per unit change of X. So a positive slope means as X goes up, Y goes up. A negative slope means as X goes up, Y goes down. The actual value of the slope is tied to the scale of these variables. So we have to keep in mind what a unit is in order to think about what a slope value actually means. Okay, with me so far? Good? All right, and let me know if the audio cuts out or I freeze or anything. I'm watching the chat to make sure, and please feel free to still, I wouldn't say interrupt with questions, but don't be hesitant to ask them. It's not an interruption. I don't like that word. So you can raise your hand or you can unmute yourself and start talking. You can put a note in the chat, whatever you'd like. And I believe both the TAs are here. Yep, there's Sam's little box and Erica's box. So you can also talk to them separately if you wish to. Or talk to each other, Just if you're going to say snarky comments, make sure it's the direct message and not the everyone message. That'd be my pro tip for succeeding in Zoom sessions here. So the fixed effect of a single predictor then. What we have is a slope, that is, the word for it is unstandardized, meaning it's in the scale of the original variables and you have to know what those units are in order for the slope magnitude to make sense. So we have results for this that include the estimate, otherwise known as the coefficient. Those are synonyms. It's abbreviated EST often. That is the optimal value for the slope, and that is found by figuring out what value would make the E's collectively the smallest. We are minimizing the sum of the squared residuals. That is the way that the betas are found. And that can be done via a matrix equation that could actually be done by hand in this case. Not that I'm going to make you do that, don't worry. We also have a standard error that goes with the slope cough, cough homework question at least 4 times, I think. Cough, 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 cough. And yes, you can search the YouTube transcript for cough, cough. I've tried that before and it is effective. It is an index of inconsistency. A standard error tells us, as a general principle, how far off the sample whatever is from the population whatever. So if we're interpreting the standard error of an intercept, it's how far off that sample's intercept would be from the population intercept. If we're interpreting the standard error of a slope, it's how far off that sample slope is from the population slope on average. So it's the average sort of wiggliness of your results if you were to do the study over and over and over again. It gives us a sense as to how to judge what unexpected means, because that is essentially our index of expected, is the standard error. So when only a single slope is in the model, the standard error is computed from a few pieces of information. Residual variance, so that is how much variability is left over in y for reasons we don't know about yet. The variance of that predictor, so we have to know the units in order to figure out the expected amount of inconsistency, and something called denominator degrees of freedom. There are 2 kinds of degrees of freedom. One is numerator and one is denominator. Up to this point, we've only talked about it as denominator. Numerator is coming in this unit. That is the sample size, or n, minus k. That you can think of as the number of slopes that could still be added to your model. That's the upper limit of how complicated your model can be. So if I only have one predictor, then k is going to be 2 because I have an intercept and I have a slope. We always have an intercept as a starting point. Once I know my estimate, what is my optimal value? Once I know my standard error, how far off is it on average from what it's supposed to be in the population, I can then compute a test statistic, hereafter known as a t-value, like this. How far discrepant from the null hypothesis I am, divided by the standard error. This then gives us a p-value directly. So this t tells us where, relative to the goalposts we are, where significance starts at t of plus or minus 2-ish. And I say ish because the exact value depends on your degrees of freedom. It is further and further out the smaller your sample. It moves in as you have more people. And because beta 1 is unstandardized, because it's in units of years per this, or pounds per this, or scores per this, to get a sense as to how, like in a more general way, we can say, is this a strong relationship or is this kind of a weak relationship? That's where effect size comes in. And there's 2 metrics of effect size that we'll deal with in this class. There's R family and D. R is correlation. So it ranges from an absolute value of 0 to 1. So it could be -1 to 0 for negative relationships, 0 to 1 for positive. And 1 is as strong as it can be. D is the other one. That is a number of standardized mean difference, number of standard deviation units apart that 2 groups are. So we'll see both of those again in this lecture. So for one slope, turns out that we can compute the standardized version as an effect size is the unstandardized estimate we get directly from the model multiplied by the standard deviation of x and the standard deviation of y. So that essentially strips off the units because beta in itself is the change in y for unit change in x. So if we take the x and y, the x's cancel, the y's cancel, and so the units are gone, and now we're left with just a correlation. Yeah, math with hands, right? This is canceling. It's also dancing. And it turns out that in this one case, if we only have a linear slope for one predictor, that standardized slope is the same thing as a Pearson correlation. But that will not be enough in most situations. We'll want to have a more complicated model to describe relationships than just one simple Pearson correlation. Is that okay? Yep. So that's my review. Changing gears then. Anything that you want to ask me about or clarify before we jump into some new stuff? We're feeling okay with this? As okay as we're going to be on a Tuesday at 2:17 or Thursday. I don't even know what day it is. I should know this. I haven't talked about it yet, but garbage day was not today. Have I told this class about that? I have not. Okay, so this is my thing. If you look on my YouTube channel, I have an avatar on there that a student made for me, and I am wearing a t-shirt that says Happy Garbage Day. There's a story behind this. During the pandemic, I taught from home for I think 2 or 3 semesters, and I taught Tuesday, Thursday afternoons, and I remembered that I had to teach on Tuesdays and Thursdays, but I had a hard time remembering which was which. Because if it were Tuesday, I said, I'll see you Thursday at the end of class, and if it were Thursday, I say, have a good weekend. So to make sure that I got that right in my head, I had to think to myself, did I take the garbage out this morning? If I did, then it's Tuesday, and if I didn't, then it's Thursday. And I realize this is a very Coralville-centric example because in other communities, garbage day is a different day, obviously. So I started just saying, Happy Tuesday, Happy Garbage Day, everybody. And that just became like my thing. So I used to joke that on my YouTube channel, like make sure you smash that like button and, buy the merch because everyone has merch. And I thought, like, if I sold merch, what would that be? And as a birthday present, 2 years ago, my husband had a t-shirt made for me that says Happy Garbage Day. And the back says lisahoffman.com. So when the weather finally cools enough to where I'm not sweating during class while teaching, I will put on my Happy Garbage Day t-shirt for you, and I'll prove it to you that I'm that nerdy. Comment, Cedar Rapids is dependent on location. Every day is garbage day. Yeah, well, that is true. If you are running the garbage truck, every day is garbage day. But Tuesdays in my neighborhood in particular, which makes me always remember not to try to go running on a Tuesday morning because no matter what route I take, I feel like I'm chasing the garbage truck the entire time and breathing in that smoke, which is never fun. But anywho, not garbage day. Happy Thursday. That's where we're at. We are at some new stuff though. So examples of when it will take more than one slope to fully describe the relationship between a single conceptual predictor and an outcome. That's the theme of this. Situations in which it takes more than one slope to describe how X relates to Y. Our first example of when that happens is when we are dealing with a categorical predictor that has more than 2 categories. So 3+ categories in a variable is going to require more than one slope to say how that X predictor relates to an outcome. So for instance, if I have just 2, this was the example that we had with binary marital status. In your homework too, this is age 3 versus 4, so drawing examples. In that case, if we only have 2 categories, we only need one slope to differentiate them. There's only one possible difference between 2 groups. So if we set up the model like this.
Olive, ¿vas a hacer café? ¿Tú quieres? ¿Vas a hacer café? ¿Tú quieres?
¿Tienes una pregunta para mí o otro? I think it's otro. But I run the mute button. So if I muted you unfairly, please let me know. Okay, there we go. So if I have my predictor centered so that 0 is one group and 1 is the alternative group, which is the way that I would prefer to set these things up, then to figure out what the model says the 0 group's predicted outcome would go like this. It turns out that it's the fixed intercept plus the slope times nothing, so it's just the fixed intercept. The difference of how 1 differs from 0 would be found as the mean for 1 minus the mean for 0, and that's just the slope. The slope then turns on if we are predicting the outcome for the 1 group. And so we can figure out via this linear combination what the model says the predicted mean should be for the 1 group. And this indeed is one of the questions that you get to practice answering in homework 2. To get this estimate, you have to ask for it with an extra piece of code. And I've shown you one way of doing that thus far that I think is instructive to describe how the process works. Once you get really good at it and it becomes tedious, like in this example, I'll show you how to do it faster. Okay. So this type of general linear model, if I have one single binary predictor, is otherwise known as a 2-sample t-test or an independent groups t-test. That is exactly the same thing as this. The t-test statistic of the beta 1 slope is your t-test of that model. It's exactly the same thing. But what if we have 3 groups? Well, we end up needing two slopes because the rationale is how many possible differences are there between groups? There's three. If I have three groups, I can have 1 versus 2, 1 versus 3, or 2 versus 3. Once I know two of the differences, though, I can figure out the third. So I really only need to do 2 because the other is then determined by what I just found. So if I have 3 categories, I'm using capital C to keep track of the number of possible categories in my predictor variable. I would need a beta 0 intercept. We always need that. And I would need 2 slopes. Beta 0 would get me to my reference group mean. Let's say that that's group 1. Beta 1 is going to tell me how different one of the other groups is. Beta 2 is going to tell me how different the other group is. And then I can figure out the difference between them as a linear combination. If I had 4 groups, then I need 3 slopes using the same logic. Can anyone guess if I had 5 groups, how many slopes I need? Yeah, finger question. 4. Yeah. And if I had 6 groups? Yeah, 5. So as a general principle, you need as many fixed effects in your model as you have groups or categories. I'm using group and category interchangeably. It's number of categories minus 1 because you already have an intercept. So it's like how many more do you need to get to the rest of the group means? And if you're thinking, hey, isn't there like a formula I learned a million years ago for how many possible group differences there are? There is. It's this one. So C, because I pronounced the exclamation point for the factorial, divided by 2 times C minus 2. So this formula will tell you how many possible pairwise differences there are between your groups, meaning between each possible pair. And this type of model, if you have more than 2 groups, is not called a t-test anymore. It's called analysis of variance or ANOVA. Yeah, formula for a combination. Thank you. I knew there was a word for it, but it's gone. So you are now going to learn analysis of variance, just in the context of the general linear model as an overarching framework for plugging these things in. Question or comment? Binary predictor is the same as the t-test. Yes. As far as I remember, t-test or ANOVA requires relatively equal group sizes, but from this equation, I don't really see this requirement. It depends on your definition of requires. So technically speaking, this approach does not require equal sample sizes. That's not a requirement from an estimation point of view. You can have differently sized groups and you can compare their means. I think what that term might be referring to is what is optimal. So if you're interested in comparing groups, you would want to have a relatively equal number of people in each group so that each of those group means is estimated comparably precisely to one another. What can happen is if you have like one group that's a lot smaller than the others, is that mean is a lot more imprecise, and it's harder to find a difference of an imprecise mean relative to some precise means. The other thing that people talk about in this context is whether or not the groups have equal variance. In the general linear model, there's only one variance. There is residual variance as one number at the end, and so we are assuming that that holds equally across groups. If that is not the case, there are workarounds for it. That's something that I will touch on at the end of the semester in terms of like things that could go wrong and what to do about them, but I'm sort of sidestepping that issue for the time being, if you can allow me that. If you're curious, though, you can fast forward to this class when I taught it 2.5 years ago. Fast backward, I guess. Fast backward to this class 2.5 years ago and look at lecture 7, I think it was. There's a little bit of stuff on that. It turns out that modifying that assumption usually takes a change in terms of estimator method. But yes, this is analysis of variance. This has been bothering me for a long time. Yeah, I'm sorry to hear that. The other thing that you have to think about in terms of group sizes is when you try to put things back together again. And there are different ways of combining things. So like these models are going to compute like a mean for group 1, a mean for group 2, a mean for group 3. And then if you wanted to compute an overall mean, it would just mean those means. Like that number won't be the same thing as the overall mean of the data because meaning the means is making the weighting different. So it's when you try to group things all back together again to get one number, whether you weight by group or not, will change your result. But that is not something that I typically would need to do in this context, because the whole reason to put group in the model as a predictor variable is to see how the groups differ. I'm not interested in lumping them back together again. I want them to be split out. Okay, good with this so far. So the idea is that I still conceptually have one x and one y, but it's going to take more than one slope to fully disentangle the effect of x and how it predicts y, in the context of groups for right now, and then in other contexts later. So here's an example. I'm going to be using a variable from the General Social Survey dataset, same dataset we had in example 1 and 2, and I'm still predicting income. And that dataset had a limited amount of variables I could pick from, so I chose one that I thought should definitely be related to income. This is a self-report question as to whether you consider yourself to be lower class, middle class, or upper class. Generally, that would be related to income, so I thought, well, that should work. So the distribution of this variable is decidedly uneven. There were 436 of the 734 people who decided that they were lower class. Note the notation here. Big N is for the overall sample size. Little n is a group-specific sample size or category-specific. That's a general convention, and they tend to be italicized. That way, when you see it in text, it doesn't look like there's just an n sitting there for no reason, like a typo, like it's deliberately set off with italics. And this is equation font, by the way, too. I can teach you guys how to write equations in Word and PowerPoint if you're interested. That's something that can make your papers look a little more professional. So the lower group has 436 people in it. The middle class group is 278, and the upper class group has 20. So these are decidedly different group sizes in this case, but I'm still going to make it work. So here's what I'm going to have to do. The rule is each predictor, if you're talking about a group, has to be binary. I'm going to create 2 new predictor variables whose job is to distinguish among these 3 groups. And the first variable I am calling L versus M, because what it's going to end up telling me is the difference of how lower and middle, or how middle differs from lower. The second variable I'm naming LVU, because that one is going to tell me how the upper group differs from the lower. So that's my intent. That's what I want the model to tell me. Given that intent, here is how I would set up these variables. I'm going to give the lower group a 0 value of each. What that does is turn the lower group into my reference. Given that a fixed intercept always tells us the expected outcome when my predictors are 0, by setting both predictors 0 for the lower group, I am saying my fixed intercept is now going to tell me the lower group's mean. I want the first predictor to tell me the difference of how middle differs from lower. So I'm going to turn that one on. You can think of these zeros and ones as like switches, like light switches. So when this variable is 1, I'm talking about the middle group. And I'm going to leave the upper group set to 0. So if I just had this column in my data right here, this would not tell me what I want to know. If I just had this column, then the 2 zeros would be lumped together in one group, and the 1 would be the difference. So to solve that problem, I add a second variable that pulls apart these 2 different zeros. Now the second variable turns on when I have an upper group, and it's still off for the other 2. So these 2 work together to disentangle the 3 possibilities of lower, middle, and upper, where lower is the reference that the fixed intercept is going to tell us about. So the equation that would go with it looks like this. We start off with beta 0 as our fixed intercept as always. I'm predicting income. I have one slope for LVM, and since I'm counting in order, I now pick up a beta 2. And this is LVU as my naming convention. So these naming conventions are entirely up to you. The way that I do it is, what is the reference and what is the alternative? That reminds me what my coding scheme means when I forget. If I focus on just the predicted value, so y hat is predicted income, that is created from the same equation, just omitting the e. So there are only three possibilities here as to what y is predicted to be. What it is for the lower, what it is for the middle, what it is for the upper. The model is going to tell us all three of those things. It's also going to tell us all three possible differences. Some of these quantities are given directly as model parameters, as fixed effects. Some of them are given indirectly as linear combinations of those fixed effects. Linear combination means do math, okay? And when I say do math, I mean make the computer do the math, not you. Because one of the things you want to know besides the answer is the standard error of the answer and the t-test of the answer and the p-value of the answer. And making the computer do the math gets you all of those things at once. You could compute all that stuff, but that would just be a waste of time. So let's work through the logic then. I have y hat for the L group, the M group, the U group, okay? So the subscript here is keeping track of which group mean I'm predicting. Question, does it matter which one you make the intercept? Nope. It's your choice. I picked the lowest one. Could have picked the higher one too. What I see people do, if they're numbered like this, that would be one way to do it. If the numbers are ordinal, the biggest group could be chosen as the reference. Like that's how it worked out here. Most of the samples said that they felt lower class. So if I predict the lower mean, the same ingredients go into it. I've got beta 0, beta 1, and beta 2. The question is, what do I plug in for the values of the group? Well, if I'm talking about the lower group, that's coded 0, 0. So I plug in 0, 0. That means the effect of beta 1 and the effect of beta 2 are switched off. I'm left with just the fixed intercept. So that's one thing the model tells me directly is what is the predicted outcome for the reference group, designated by saying that's where it's zeroed out. So that's a choice that you get to make. The middle mean and the upper mean are found as linear combinations. So they both still start out with the beta 0, which is what the lower group is. Beta 1 switches on if I'm talking about the middle group. Beta 2 switches on if I'm talking about the upper group. The others are switched off. So if I work through the math here, the fixed intercept plus the slope for middle tells us what the mean for middle is. The fixed intercept plus the slope for upper tells us what the mean for upper is. Then the three possible differences. Now that I know how the model tells us what the mean is for each group, all I got to do is subtract, and I know what the mean difference is between the groups. So lower versus middle, that means that I'm saying lower is my reference group, and I want to know how middle differs from it. So to make that direction work, I start with middle. We already know from up here that the mean for middle is found as beta 0 plus beta 1. We already know from up here that the mean for the lower group is just the fixed intercept. The two beta zeros cancel, and you're left with beta 1. Same thing happens in differentiating lower versus upper. The mean for upper is beta 0 plus beta 2. The mean for lower is still beta 0. Beta zeros cancel, you're left with beta 2. So this is a long-winded way of saying the slopes directly tell you these two particular group differences. Beta 1 is how the middle group differs from the lower group. Beta 2 is how the upper group differs from the lower group. So here's my three model parameters and what they tell me directly. But there's one thing I don't yet know that I would probably want to know, which is what about the two non-reference groups? How do they differ? Well, same logic will get me that. I have the mean for the upper minus the mean for the middle. Now the beta zeros cancel, but I'm still left with beta 2 minus beta 1. And that's how I get it. So this one you are going to have to ask for specifically because it is a linear combination of existing model parameters. It's indirectly given by the model. And for extension of this, I will quote your textbook. They have a lot of additional explanation beyond this. I'm going to reload and pause to ask for questions. How are we doing so far, folks? Couple thumbs. Black boxes, you can do the thumbs too. Or give me a poop emoji. You know, whatever you're feeling like. There's some thumbs. Question. No, thumb. Yeah, the icons look very much the same. But yeah, thumbs up in the chat, that works too. Yeah, they have lots of fun emojis. I learned they do have a thumbs down, actually. So that is a choice in Zoom. They don't have thumbs sideways yet, to the best of my knowledge. But, okay. So the idea here, we have to differentiate our three groups via two new predictors, each of which is binary and acts as a switch to flip it on for an alternative group relative to a reference. But the model tells us still what the mean is supposed to be for each group, and therefore the model tells us still all the mean differences that there could be. So here's what's going to happen in the results. So the way this is set up is like, here's the end of the process. I will show you via a handout that will start later on, like what the code is that generated all these things. But I want to focus on interpretation and just say, look, numbers. So in this data set, we have an empty model to start with. The mean for income is $17.3 thousand. The variance of income before we add any predictors is 190. Okay, so that's our starting point. Now we can add in the effect of working class. So conceptually, to me, this is one idea. Which class did you pick is one variable in your data set. But I had to turn it into two predictor variables, each of which is binary, to get this to work. Ooh, we got one. I like that. We're having fun playing with emojis. So it ended up that beta 0 was estimated as 13.65. Given my coding scheme, beta 0 is when my x's are 0. That is the mean for the lower group. So people who said that they belong to the lower class group make on average $13,650. These are in thousands. The standard error for that intercept is 0.63. So that is how wiggly the mean for the lower class group would be expected to be, how far off from the population version you are on average across multiple samples. So this is like a replicability idea of the standard error. That is significant at p less than 0.001, meaning that 13 is not 0. So that's a result we would not typically care about in terms of significance. Slope 1 was estimated as 8.85. Slope 1 tells us how the middle group differs from the lower group, specifically because this other variable is still in here helping to differentiate the two kinds of zeros. The standard error for slope 1 is 1. So on average, we would expect this mean difference of how middle differs from lower to vary by 1 across samples relative to the population mean. Now this is p less than 0.0001. What do I compare this p-value to decide whether or not it's significant? What's my standard for declaring significance? 0.05? Yeah, in general, it's your alpha level. So it's you decide this a priori, meaning beforehand. That's what that means. A priori, beforehand, you say, here's my line in the sand. I declare it to be 5% expected, 2.5 on one side, 2.5 on the other. And if this p-value is less than 0.05, I would declare this as significant. Question, is this intercept still compared to 0 for significance because of the categories? No, as a general, like the default hypothesis test you get for every parameter, regardless of what it means, is a test against 0. So that's a universal thing for any fixed intercept, regardless of what else is in the model. Yep. So we do care about this one. So I have a significant slope, and it is a positive number. So in your drop-down menus, I would label this as significantly positive. This means that the middle group makes more money significantly than the lower group. How much more? $8,850 on average. Beta 2. Same idea, different reference. Now we're talking about how upper differs from lower. Upper differs from lower by almost 11. $11,000 differentiates the high group from the upper group from the low group. Now look at this standard error. It's 3. It's 3 times as large as the standard error for the other slope. Is that a typo? Or is that a consequence of something? Could be a typo, I could be imperfect, but in this case it's not. No, the sample size is small. Ding, 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 that's it. So, oh, I had it on the slide. I knew I was going to make this point. There's only 20 people in the upper group. I have like no idea what their mean's supposed to be. It's a very imprecise number. So if I'm not sure what the mean for the upper group should be, it's kind of wiggly, more wiggly than the other group's means. That means the mean differences are wiggly too. So we have less certainty the smaller the group size. In this case, though, we can't control that. This is a measured variable. The groups are as they are. So even though the standard error is much larger, it still crosses the threshold for significance. It's still outside the boundaries. So 11 divided by 3 would give me the t-test statistic that this p-value was based on. 8.8 divided by 1 would be my t for the first slope. And my residual variance, the variance of the e's that remains after factoring in which group someone's in, is down to 171. So we have explained part of the reason why people differ in income with what group they call themselves. Now, explain is a very generous term. These two variables are associated. But explained variance is what people call the reduction in E variance. Would we get the same SE, which regardless of which value is the reference? It depends on which E you're talking, which SE you're talking about. So at the end of this, each group has a mean and an SE. Each possible mean difference has an estimate and an SE. So if you're talking about those, like, then no. But if beta 1 differentiated like 2 versus 3, then yeah, its SE would have to change because it's based on different information. Yep. In terms of your conclusions, like the big picture of what you're doing, that will not change based on which reference group. Like the residual variance is going to be 171 regardless of whether the lower group's the reference, the middle, or the upper. How you get to the end result depends on which reference group you are, but the parameters will just rearrange themselves to tell the same story if you choose a different "you are here" sign for your data. Okay, so we're missing 3 things. What we know so far from the intercept is what is the mean for lower. Beta 1 for the first predictor tells us how middle differs from lower. Beta 2, the slope for the second predictor, tells us how upper differs from lower. So we know 1 mean out of the 3, and we know 2 mean differences out of the 3. Let's get the rest of them. So if I fill in the patterns here, fill in the fixed intercept, fill in the fixed slopes, plug in my zeros and ones for the other groups that turn each of those slopes on or off. Here is the result. So the predicted mean for the middle group is 22.5. The predicted mean for the upper group is 24.63. Note the difference in the standard errors. So the same idea here. The upper group is a lot wigglier in terms of what its mean would be across samples because it's only 20 people. It really depends on which 20 you get. And the mean difference of middle versus upper is beta 2 minus beta 1. That works out to be 2. As you can see by doing a rough eyeball math here. 2 is the estimate. The expected wiggliness across samples of that estimate is 3. So this is a case in which there is more expected variability than what the size of the effect is. So it's well within expected territory in terms of expected wiggliness. The corresponding p-value is 0.48. In English, that would mean if the null hypothesis were true, if there is no difference between the middle and upper groups, we would see a difference of 2 or greater 48% of the time. How often would we see this result if the null hypothesis of 0 slope were true? That's what your p-value tells you. Okay. Sorry, my mouse is going into the chat trying to type things, and I swear I didn't do that, so it's okay. All right. So we don't have a significance test for M versus U in this model. It depends on what you mean by model. Directly, we do not. Indirectly, we do. So I can draw an analogy, dating myself. When I took the GRE to get into graduate school, there was a test called the logic part. So we didn't do writing. We had words, math, and logic. And the logic section was filled with puzzles like if Bob is 12 and Sam is twice as old as Bob, but he's half as old as someone else, like how old is this person? And you're given these like breadcrumbs and you have to work your way through the logic to figure out how old each person is in the puzzle. Like I think of the model parameters as the pieces of information you're given. The end result of working through the combinations to get to the answer is still part of it though. You can still get there. Sorry if I missed it, but how did you get 3.03 for the mean diff of M versus U? So let me go back to the logic. So we start with how the model tells us what the mean is for each group. And that comes from building the equation for a predicted y, where we plug in the predictor values for each of the slopes that go with that predictor. So for instance, I know the middle group has a mean formed by beta 0 plus beta 1. I know the upper group has a mean formed by beta 0 plus beta 2. If I literally take those chunks and subtract them, upper mean right here, middle mean right here, their difference is found as beta 2 minus beta 1 after you cancel out the redundant intercepts. So this is indirectly given by the model results, but it's based on the model results. You can get there through the logic of the system. So that's how I got the 2.13. And I had to ask for that in the software because it doesn't give you these kinds of combinations by default. You have to ask for them. And I did not learn how to get that until way too late. Like I was on the tenure track by the time I learned that, and I wish I would have had it sooner. Do you know how I learned how to get the missing mean difference? If I didn't know how to ask for it and I had to get it out of the model, what could I do to make the model tell me directly via its slopes how upper and middle differ? Any guesses? I can hand calculate it, but I don't know how to get the p-value. Yes. Think about how I can hack the model. This model tells me middle versus lower and upper versus lower because I set lower as the reference. What if I set middle as the reference? Could I do that? Sure I could. Then I would have a parameter that directly tells me upper versus middle. So it's a workaround. You rearrange things until you get what you want. But that gets annoying real quick if you have a lot of groups and you don't want to have to rerun the model with each permutation to get all the pieces. So getting it all out of one model is much more efficient. And the good news is if you ask for it in the software, not on your calculator, then you do get the standard error that goes with it, the t that goes with it, the p that goes with it, and I'll show you how to get the effect size that goes with it, all in one fell swoop. Pretty cool, huh? You're like, yeah, no. No, it's hip to be square. Remember, that's our theme song from me for this semester. Quant is cool. If you're like, yeah, I hate equations, can you show me pictures? I got you. So this is a tricky picture, but I'm trying to put everything in it. So let me see if this will work. So I have my y-axis. This is predicted income. Now my x-axis would typically be numbers, right? Like we had, education on the bottom and income as the y-axis. Well, in this case, I got to draw it a little differently. What I have on the x-axis are two different x-axes, differentiating lower, middle, and upper. So the first variable differentiates middle from lower. The second variable differentiates upper from lower. So that's where the lines are drawing the way they are. So if I start with the lower group, its mean is 13.65 as given by the fixed intercept beta 0. So I've got my fixed effects up here for reference. I've got my coding scheme up here for reference. and this is y hat as predicted by the model. So if I follow the change in y for a 1 unit change in x in red here, so moving from the middle group, starting from lower and heading to middle, that's my 1 unit change in this x. The corresponding change in y is shown as the increase in the y-axis relative to that. So that is my difference of how middle differs from lower of 8.845, or 54, excuse me. If I do the other x-axis, if I go from lower all the way to upper, this is still a 1 unit change given my coding scheme. And so I have the corresponding change in y as the length of this blue line right here, which is 10.985, the slope of beta 2. Well, I can then figure out, like if I start with 13.6 and I add 8.8, I get to 22.5. If I start with 13.65 and I add 10.985, I get to 24. And then I can compute the difference. So I know that if beta 2 gets me all the way up to 10.9 and beta 1 only gets me to 8.8, that little difference right there, that's the missing slope that I don't have. Thank you. 3 dimensions in 1 plot. This is the upper limits of my graphics capability, by the way. This is it. So beta 2 minus beta 1 is the 2 that I get. So we can get all 6 numbers out of just the 3 that are given, because they're all related to each other in this systematic way. And this set of triangles would stay the same regardless of who my reference group is. It's just then things would be moving down instead of up and vice versa. Okay, I don't want to do that one yet. All right. Questions? Let me show you a 4-group example. Let's say that I have an experimental study designed to compare the efficacy of 3 alternative new treatments to some kind of business as usual control. That's a common sort of thing in medical settings, for instance. Well, I got 4 groups. How many slopes do I need to differentiate my 4 groups? This is a finger question. 3. Yep. Because I already have 1 intercept, and then adding 3 slopes gets me to 4 fixed effects, and I've got 4 groups, it'll work. In this context, it is very common to set the control group as the reference, like what would happen had I not intervened, and then to talk about the effect of each treatment via its own variable. So I'm going to call these D1, D2, and D3 for differences due to treatment, whatever naming system you want to do here. So this is the effect of treatment 1 relative to control, treatment 2 relative to control, treatment 3 relative to control. This particular coding pattern is known as indicator coding, or dummy coding is what it's sometimes called. Dummy variable is the same thing as a binary variable. That's a term people use. They're not meaning to be offensive. I know it's not nice to use the word dummy in most contexts, but that is really accepted. So indicator coding maybe is better. So the model would look like this. So another way of saying this is that I am running a one-way analysis of variance with 4 groups. That's what this is. So the model is going to give us the predicted outcome for each category, for each of my groups, like this. Beta 0 is what happens when all the slopes are set to 0, so that's my control group mean. Beta 1 turns on this slope if I'm talking about treatment 1. Beta 2 turns on its slope if I'm talking about treatment 2, and so on. So just take a moment and stare at this plot and see if you can follow it. And if not, please ask questions. As I'm kind of shortcutting the logic a little bit. The idea is that if it's treatment 1, then only this variable is relevant. If it's treatment 2, only this variable is relevant. The others will zero out. So if the model tells us the mean for each group, the model has to tell us the mean differences across them as well. 3 are given directly. I've got control versus each of the 3 treatments. That's going to show up in my output. How many other differences are there that I might care about? And feel free to read from the screen. Or type from the screen, as it were. I've got 3 mean differences given to me directly by the model via these 3 slopes. How many more mean differences between pairs of categories? Yeah, the differences between treatments. I might want to know if treatment 3 is better than 2, and if 2 is better than 1, and if 3 is better than 1. So there's 3 more. Good news, they're in here. They're in here too. So I'm throwing some numbers in here to help us keep track of things. Let's say that what happened is the control group is 10, the treatment 1 group's mean is 12, treatment 2's is 15, treatment 3's is 19. Here's how the model tells us, via the fixed effects, intercepts and 3 slopes, how those means came about. So first, control versus treatment 1. The alternative group is treatment 1, the reference group is control. Beta 1 is directly going to give me the difference between control and treatment as 2. And it's a positive 2 because the slope always tells us how the 1 group differs from the 0. Likewise, control versus treatment 2, directly given by beta 2. That would be a coefficient of 5 to differentiate these two. So beta 2 has to be 5 to make up this mean difference. Likewise, beta 3 would have to be 9 to get 19 versus 10. Yes, combinatorics. I have them memorized up to about 6, and then after that I can't do it. Treatment 1 versus treatment 2 is not given directly by the slopes, but it's given indirectly by comparing them. So if the treatment 2 group mean is this right here, the treatment 1 group is this one right here, I do the math. The beta zeros cancel, and I'm left with beta 2 minus beta 1. That works out to be this difference is 5, this difference is 2, the difference of the differences is 3. So stare at that for a second and let that sink in. Likewise, treatment 1 versus treatment 3. Same idea, different slope is the ingredient. Now it's beta 3 minus beta 1. Treatment difference of 9 for the first one, treatment difference of 2, the difference of the difference is 7. And last but not least, 2 versus 3, found the same way. So I only need 4 parameters to recreate all 6 differences. Yeah. At this point, in some classes, we would start talking about alpha family-wise error rate from doing these multiple comparisons. I'm not doing that in this class. I'm just not. I have to decide what to make time for and what I feel is ancillary, and that falls into the latter category. There are folks that would look at this and say, you can't do that! You can't do all the comparisons and have each at 0.05 because that's alpha inflation. Is that the next class after this one? It'll be in design of experiments. I believe Ariel covers that. It will not be in my next classes. I have 2 reasons for that. Number 1 is that which group you set as the reference is arbitrary, right? We decided that. The model, like if I decided to make treatment 1 the reference, the slopes will just all reconfigure to capture the differences relative to that as a new reference point, but the means are still going to be the same. Like the model can't change the data. So it is just an arbitrary coincidence that these are the 3 differences we get directly, and these are the ones that are after the fact. So I don't view these 3 as like more special or privileged or protected from alpha inflation as the 3 that we have indirectly, because they are an arbitrary assignment. The model tells you all of them. If one of these means is sort of like like if the mean itself is like a problem, like it shouldn't be that high, it's like an error, then any comparison to it is also going to be suspect, but we can't know that in advance. That's one reason. Arbitrary reference group creates a different version of the same results in terms of what you get directly versus indirectly. The other reason is because this is only a thing in this very, very specific ANOVA context. If you have a general linear model with 6 slopes in it, and the slopes are for quantitative variables, no one will care at all about alpha inflation, even though it is the same exact problem. And when you get into more complex multi-level models, as the other courses I teach, structural equation models with latent variables can have hundreds of parameters in them at the same time. No one says a word about alpha inflation there. So to me, it's an arbitrary thing to think it's really important in this one specific context, but not in all the others. I have a general philosophy. If you are worried about being too lenient, what do you think you should do? If you want to be cautious about false alarms, what's the solution?
Smaller alpha.
That's it. You control this. If you set your alpha at 0.05 ahead of time, you're expecting that 1 in 20 true null hypotheses would be significant by chance. If you're going to be doing 20 comparisons in one model, one of them's wrong. And there's actually a higher probability of that if particular comparisons are tied to particular means, and then those particular means are the problem. But as a general principle, like if you know you're going to be doing a lot of tests, bump down your alpha. Make it more strict. Make it harder to have a false alarm. That is a philosophy that works pretty much no matter what you're doing. Let me set up what's coming next, but not go there. Can we agree to that? Since it's 3:04, and I know for a fact that Zoom attention only lasts so long. I've been on Zoom all day, it feels like, so. Okay. So this is lovely, right? There's all these results, there's all these different numbers, there's all these p-values. Like coming back to the actual story we had. One more. Oh, yeah, this slide, right? So I can talk about this mean is different than that mean, and this group's different than that group, and the whole thing. But what I don't have a general sense of yet is how related is class membership to income as a whole. Like research questions are written at this generally higher level most of the time. How important is self-related status in predicting income? Like that would be the research question that motivates this analysis. Okay? I don't have an answer to that yet. It's like, well, I got this one and 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 this one. Like, that's not the answer. So what we're missing is the forest, right? I'm down on the ground in the trees, maybe even down in the bushes. We're missing the forest. So what's coming next is trying to put this back together again as some kind of composite effect that tells us how useful this variable is that took multiple slopes to describe it, but putting them back together to say, hey, does this predict income or not? And if so, how well does it do? Where that is going to take us is R square for the amount, or proportion, of variance explained, and a new letter to add to your collection of hypothesis testing. You're like, oh, another letter? Yay. We've got most of them right now. We've got B looking things, we've got A looking things, we've got E looking things. We're going to pick up F. We're going to pick up a new letter. And you're like, you mean the F from ANOVA? Yep, that's where we're going. It's called the omnibus F test because it sounds fancier that way. And F is going to be a significance test that says, hey, can you just like stack all these slopes together and tell me if they're significant as a set? That's what F does. And then a corresponding effect size would be by how much did the residual variance decrease? What proportion of it has been reduced by putting in the multiple slopes that it took to delineate the effect of this predictor? That's R square. squared units because we're talking about variance, which is in squared units. So I'm seeing some nodding. F is familiar to some folks. Things you've heard before. Black boxes, is F familiar or no? This is a thumbs up or thumbs down for anyone who's still with me. I'm back to dancing. F. Okay. So for the thumbs down folks, I'm going to give you an analogy next week. F tells you whether you got a good deal. Like if you go shopping at a store and you're searching the clearance racks and you want to get the best deal possible, I have a whole analogy about how F is an index of how good of a deal you got. I'll save that for next time though. But I'm trying to set the stage to connect this to things you may have heard in the past. And if you haven't heard it before, then you get to hear it for the first time. All right, 308. Would you like 7 minutes of your life back as a bonus? No one's going to say no to that. Any questions before we adjourn for the week?
My question is, with something like this, with the lower, middle, and upper self-disclosed, isn't that really much harder to do than if you made your own category and just called it lower, middle, and upper and not worked with quantitative? Even though if you had a quantitative, you probably want to do it with quantitative data.
I'm not sure I understood the question. Can you try again?
So in other words, because of your background,
Mm-hmm.
maybe you think making $80,000 a year is a
Mm-hmm.
lower,
Yeah,
class
this is
person
subjective. Mm-hmm.
versus, in Iowa, they say, "Oh, I'm middle,"
You can live pretty good
or
on 80 in Iowa. That's part of the reason I live here, quite frankly.
well, exactly. Or like in New York, $80,000, you're living in a box.
That's correct. Okay, so I agree with you, but what is the question as it relates to this then?
Would it, if you were actually gathering the data, would it be better for you to actually have real values
Ah,
versus, and if you choose to make a category called lower, a category called middle, and a category called upper, and try to lump them together like that yourself versus someone saying my number is whatever because of where I live.
yeah, so that's more of a research designy kind of question. I agree with you that the perception of class status is entirely subjective and also cost of living dependent. I would probably approach this by adding additional questions to the survey. So I'd be like, what do you consider the amount of money you need to be lower class or middle class or upper class? And then you could ask them the same question, but then you could contextualize it a bit and be like, okay, relative to this as my personal baseline, this is how I think I am. And then you could probably get a little more information about that kind of subjectivity, but it would take additional questions formatted a different way to get there.
Thank you.
You're welcome. Anyone else? All right, then let me know if you need anything. Homework 2 is due Wednesday. Have good weekends. Thanks for being here. Bye for now.